Everyone, my name is Melcher Esparilla. Welcome to my animation video. In this video, I created an animation to explain the process of finding all odd numbers in an array. But it's that not all will also analyze the time and space complexity to understand how efficient the algorithm is.
Hi everyone. Welcome to this video, where we're going to learn how to find all the odd numbers in a given array using an efficient algorithm. To find all the odd numbers in a given array using an efficient algorithm. Let's assume we have this array, 4, 7, 10, 15, 22, 27, 30. Our goal is to extract and return all the odd numbers. First, initialize an empty list _numbers equals. Second, loop through each number in the array. Third, check if a number is odd using modulo, %. Fourth, if odd, add it to the list. Fifth, return the list of odd numbers. After running this algorithm, we get the final result, 7, 15, 27. These are the odd numbers in our array. Section 2, Time Complexity Analysis. First, initializing an empty list O1. This operation runs instantly, regardless of the array size. Second, looping through the array On. Since we iterate through the array once, this step takes On time. Third, checking if a number is odd O1. Modulo, % is a simple arithmetic operation that runs in constant time. Fourth, appending an element to the list O1. Adding an element to a list takes constant time for each odd number. Fifth, returning the final list O1. Returning the list doesn't depend on the array size, so it's O1. Total complexity equals O1 plus On plus On plus On plus O1 plus O1. Simplifying equals O3n plus 3 equals On. Final big O notation, On, since 3n plus 3 simplifies to On. This graph represents how the space usage changes as we process each number in the array. The x-axis shows how many elements have been processed, and the y-axis shows the number of. If we visualize space usage over time as we process each element in the array. The space starts at On, for storing the input array. An empty list uses O1 space initially. Space usage increases only when an odd number is encountered. Even numbers do not increase space usage. The final space used is OK, where k is the number of odd numbers stored. In a graph with x-axis representing elements processed and y-axis representing space used, we observe flat regions when processing even numbers. Step-like increases at indices where odd numbers are added, for example, at positions 2, 4, and 6 for 7, 15, 27. The total space complexity of our algorithm is determined by adding the space used at each step. First, the input array of size n is stored in memory, contributing On space. However, since this array is given as input and not duplicated, it is not considered extra space. Next, we initialize an empty list to store odd numbers, which takes O1 space. During the iteration, we use a single loop variable, which also consumes O1 space. As we extract odd numbers, we store them in a new list. If there are k odd numbers in the array, this list requires OK space. Finally, returning the list of odd numbers also requires OK space since the function outputs the stored values. Adding up all components, the total space complexity is On plus OK plus O1 plus O1 equals On plus OK. Since O1 is negligible, the final result simplifies to On in the worst case, where all numbers are odd, or OK in general cases, where k is the number of odd numbers extracted. Thanks for watching. If you found this helpful, don't forget to like, share, and subscribe for more easy-to-understand algorithm insights. See you in the next video.
Thanks for watching. Please subscribe.